Hi everyone, I am Dr. Baby Shalini, Associate Professor, Department of ECE, Rohini College of Engineering and Technology. In this video lecture, we are going to see about Hartley Oscillator. Hartley Oscillator is a type of LC tuned oscillator, which means in the feedback network we are having L and C elements. So this is the circuit diagram of Hartley Oscillator. So which consists of a voltage divider bias transistor network, and into that in the feedback connection we have connected two inductors L1 and L2, and which is connected in turn with the capacitor C. So the Hartley oscillator consists of two inductors and one capacitor in the tanked circuit. So now the Hartley oscillator consists of three elements in the feedback network. We can take it as Z1, Z2 and Z3. So Z1 is nothing but the inductance L1, and Z2 is nothing but inductance L2, and Z3 is nothing but capacitor C. Now CE is a bypass capacitor, and CC1 and CC2 are coupling capacitors. The feedback network consists of three elements which determines the frequency of oscillation of the Hartley oscillator. So next, let's listen to the operation of the circuit. When the supply voltage plus VCC is switched on, the transient current is produced in the tank circuit, and consequently damped harmonic oscillations are set up in the circuit. The oscillatory current in the tank circuit produces AC voltages across L1 and L2. As the terminal 3 is connected with ground, it is at zero potential. If the terminal 1 is at positive potential with respect to 3 at any time, then terminal 2 will be at a negative potential with respect to 3 at the same instant. Thus, the phase difference between the terminal 1 and 2 is always 180 degree. In the CE mode, that is common emitter mode, the transistor provides the phase difference of 180 degree between the input and output. Therefore, the total phase shift is 180 degree. So the tank circuit produces 180 degree phase shift and the transistor produces 180 degree phase shift. So the total phase shift is 360 degrees. Thus, at the frequency determined for the tank circuit, the necessary condition for sustained oscillation is satisfied. And if the feedback is adjusted so that the loop gain A beta is equal to 1, then the circuit acts as an oscillator. So now the frequency of oscillation that is determined from the circuit is F0 equal to 1 by 2 pi root LC, where L is the total inductance of L1 and L2. So that we can write L is equal to L1 plus L2 plus 2M, where M is the mutual inductance between the coils L1 and L2. Mutual inductance means that whenever current flows through one inductor, it induces some EMF in the another conductor or another inductor. So that since we are having two inductances, that's equivalent inductance is L1 plus L2 plus 2 times mutual inductance. Now the condition for sustained oscillation is HFE should be greater than or equal to L1 plus its mutual inductance dividing by L2 plus its mutual inductance. In the Hartley oscillator, Z1 and Z2 are inductive reactances and Z3 is the capacitive reactance. So when we write its equivalent impedances, Z1 is equal to j omega L1 plus j omega M, and Z2 equal to j omega L2 plus j omega M, and Z3 is equal to 1 by j omega C, where 1 by j can be replaced by minus j, so that it is equal to minus j by omega C. Substituting these values in oscillator equation, we will get HIE into the total impedances Z1 plus Z2 plus Z3 plus Z1 Z2 into 1 plus HFE plus Z1 Z3 is equal to 0, When we substitute all these Z1, Z2, Z3 values in this equation, we will get L1 plus L2 plus 2m minus 1 by omega naught square c is equal to 0, where omega naught is equal to 2 pi f or f naught is equal to omega naught by 2 pi. So when finding its value, we will get f naught is equal to 1 by 2 pi into root of L1 plus L2 plus 2m into c. So this is the frequency of oscillation produced by the oscillator. Thank you. So the condition for oscillation is HF is equal to L1 plus m dividing by L2 plus m. Thank you.